Okay, good morning, everyone. Sorry about the delay. Just Zoom was giving me a hard time. All right. Okay, today we are going to finish chapter 2, the last section, that continuity, and then we start chapter 3 today. So section 2.6 is a relatively simple section, continuity. So first, what does it mean for a function to be continuous? So the idea is that the following. That's a very intuitive idea. The function is continuous. Basically, it means when you start sketching its graph, you never lift your pencil off the paper. You keep going, going, going. So that's really continuity. You sketch it, you keep going. You never stop and pick up somewhere else. So that's continuous, and that's something that's not continuous. That's vaguely the idea. But we need to define this properly. So, definition, we say that a function f. So we have a function, it has an input and an output. So we say that f is continuous at a point A, so at an input point, so this is my A, that's a point A. We say that the function is continuous at this point if the following conditions are satisfied. First, the function should be defined at this point. So we want an output here. It cannot be just an asymptote. It cannot be a whole. The function should have an output here. Also, we need that the limit, when x becomes close to a of f of a, we want this limit to exist. Remember, when we compute limit, we don't care about the point a. We care about what's happening near a. We want the limit to exist, not only exist, and we want the limit to coincide with the value of the function, to be equal to the value of the function. So we want the function to be defined here. When we approach the function from left or right, we should approach the same number. Not only that, we want this number to be the value of the function here. So it means we want the function to approach the number like this and like that. There is no jump or whatsoever at this stage. So that's a picture of continuity. So for example, a lot of the functions we deal with are actually continuous whenever they are defined. So suppose I take the function f of x equal x squared, our basic function. Now this function, of course, there is no issue with it is continuity. So if I take any point, let me take -2. The function is defined at -2. And the limit from the left and the limit from the right will coincide with the value of the function. So a lot of the function we deal with will really have this nice property, but not, of course, all of them. So suppose basically you want to see how can a function fail to be continuous. So we need to introduce a word. We say that f is discontinuous. Discontinuous at a point A if it's not continuous at this point. If f is not continuous at this point. Okay, so we say that f is discontinuous if it's not continuous at this point. So how can a function be discontinuous? So let us study this. What are the scenarios? Okay. So how can a function be discontinuous? So let us see a graph. So how? Okay. So let's see how this can happen. First, one scenario is the following. This is a point A, and the function does this. F is not continuous at A because it does not satisfy f of A defined. So we need three conditions to be satisfied. So the first condition is not satisfied. So here f not continuous because f is not defined. F discontinuous because f of A is not defined. Okay. Now let us take another example. Suppose my function look like this. So that's one important scenario. Okay, it's defined, but then it goes like that. This is not continuous. Why it's not continuous? F of A is defined. Now which condition of this continuity is lost here? 1, 2, or 3. So that's my graph. And these are my conditions. Which condition is lost in this scenario? Very quickly.
2.
2. Absolutely. The limit actually 2. The limit doesn't exist. The limit does not really exist. So here f is discontinuous because the limit does not exist at A. Because the limit as x become close to A of f of x does not exist. Right limit, left limit are not the same. So the right limit and the left limit are different. Okay. Now there are other scenario where it could be also, let's see in last scenario. So the function can look something like that. It has a hole. So these are like odd kind of cases. They occur very seldom, but we have to look at them. So this is my point A. Now why f, the function is not continuous? We go through the list. F of A is defined. That's the output at A. The limit as x goes to A, does it exist? It's 2 satisfied here. It's 2 satisfied. Does the limit exist? This is your picture. And the question, does the limit exist? What can you say? Yes, Elizabeth say yes. Anybody agree with her? Remember, limit, we don't care what happened at the point A. We care what happened near the point A. What happened at A is really meaningless for us for the limit. So definitely the limit exists. Whatever this number is, that's what the limit is. No, but not only that. We want the limit to coincide with the actual value of the function. And that's really what's failing in this scenario. So not continuous here. This continuous because the limit, even though we have a limit, but it's not equal to the value of the function. Okay, so that's really a kind of how a function failed to be continuous. First, it's not defined. Absolutely crucial. Second, there is this jump. Third case is we have this hole, but the actual value of the function is obtained in another place. As I mentioned, most of the function we work with will be actually continuous on their domain. So let me see what do I mean by all the most of the functions. So let us say f of x equal e to the x. This function is absolutely continuous for all x. F of x equal ln of x. This is continuous for which value of x, for example? It has to be continuous in its domain. The log is defined only for x positive. So that's, for example, for only x positive because that's its domain. Let me take f of x equal 1 over x. Okay. And is this function continuous for all x's? Is there a place where this function may give us issue? Continuous, is it continuous for regardless what input we put here, except at 0, of course. Except at x equal to 0 because it's not defined. I mean, so the function is not even defined, and that's really where we have this graph. Okay, so but most of the function, as I said, will be, except of course some. Let me take a graphical example before I define the idea of. Actually, let me define the idea. No, let me take that. So a graphical example just to sum up all the three cases we talked about. And the question is simple. Find all the points of discontinuity of the function f. So all the points where this graph, where this function given by this graph is discontinuous, give me all the points and the reason behind the discontinuity. So get started. So find all the points of discontinuity. Where is this function given by this graph discontinuous? Go on. At 2, at 0, obviously discontinuous at 0. At a equal to 0. Why discontinuous? Because this is the scenario where the limit doesn't exist because left limit, right limit are different. Does not exist because right, left limit are different. Another point of discontinuity 2. So f discontinuous at 2 because f is not defined at 2. Okay, that's the reason for discontinuity. Is there any other place? Okay, 4. F discontinuous at x equal to 4. F is discontinuous, sorry. At a equal to 4, at x equal to 4, because, and that's really the hardest one in a way, but it comes up. I said seldom, very seldom it comes up. So it's not continuous here because f of 4 is defined, but the limit, which is whatever the value here, that's the limit, does not coincide with the actual value of the function. So f discontinuous x equal to 4 because the limit as x becomes close to 4 of f of x, even it exists, is not the actual value of the function f. Okay. Now there is a notion of what we call right or left continuity. So let me explain what this means, and then I will go back to the example. Intuitively, we say that a function is left continuous at the point, left continuous, if, of course, the function is defined at the point and the limit from the left coincide with the actual value. Okay, so I'll write it so you guys can absorb it, and then I'll take back. Sorry, let's go. Okay. So we say that f, so definition. Okay. We say that a function f, we say that f is left continuous. Left continuous at a point A if, so left continuous, if the function defined at A, so f of A defined, so we definitely need an output there, but only the left limit coincide with the actual value of the function. So we don't care about what's happening from the right. So that's what left continuous is. Similarly, we define right continuous. At a point A if, again, the function is defined, so there is meaning, there is an output here, and the limit from the right coincide with the actual value. Okay. So in my mind, when I'm thinking left continuity, I'm thinking this way. This is a point, there is an output, and the limit from the left coincide. That's left continuity. I don't care about what's happening from the right at all. Right continuous is the same thing, but from the right. This is the point A, the function. The limit exists, it coincides, and what's happening from here is absolutely nothing I care about. Okay, that's left and right continuous. So if I go back to my graph here, and the question is, for each point of discontinuity, decide if f is right, continuous from the right, from the left, or neither. It means it's really not, it's discontinuous, period. So we start with each one of them. X equal to 0. Is this right continuous, left continuous, or neither? Quickly. We go through the list. Left continuous, Elizabeth, anybody else? I agree with her. Let's go through the list. F of 0 defined, that's at least we need that for continuity. So f of 0 defined, absolutely defined. We have a meaning. Okay, second, the limit from the left, and the value, so suppose this is, I call this 2, for example. The limit from the left and the value of the function coincide. So left continuous. So the limit from the left of f of x is equal, and that's really what we need, to the actual value of the function. So definitely left continuous. Now 2, neither. 2, the function is not defined. We're done. We move on. We don't even think about anything else when the function is not defined. 4, the function is defined, but neither the left limit nor the right limit coincide with the value. So this is a function which is not left continuous and neither right continuous, end of the problem. Okay, so 0 is neither. So sorry, a equal to 2 is neither. A equal to 4 is neither. Neither one is continuous. Okay. So I finished this section about continuity with one last example. And here we are. Again, a simple example. There is nothing really hard here. Okay. And I say I take the following function. So obviously, from what we say, you know, discontinuity when there is a jump. And most of the time we have a jump when the function is piecewise defined. That's really the case. So now I ask you the following question. It's not a graph this time, it's just a function given by rules, which change with the domain. And my question is, okay, for x less than 1, this is like a nice parabola. So there is really no issue with that. For x bigger than 1, it's a straight line. So if this function will have a problem, it has to be when the function, the formula is changing right there. So now my question is f continuous at a equal to 1? I'll give you a minute to figure it out, and then you guys let me know. So you can write it up and then figure out, and you have to remember all the 3 conditions of continuity, all of them.
Should we graph it first, or are we doing it?
No, good question. No, you don't, I don't want you to graph it.
Okay.
Very good question. No, I just want you really to study it. What's happening at 1? Is the function defined? Does the limit exist? Does it coincide with the value of the function? But I want you to spend a minute yourself figuring it out, and then we'll take it on the board. Definitely no graphing. Any input? Not left continuous, not continuous. Okay, I want anybody beside Elizabeth, and then I will take on, because you guys have to justify what's really happening. Anybody agree with her or disagree?
I agree.
I agree. Okay, anybody else? Okay, Morgan, not continuous. Okay, now let us go through the list. No, very nice. Now, why not? Step by step. Is the first condition defined? Step by step, we go to it. So here, so yeah, the point is 1. Is f of 1 defined? Oh yeah, f of 1 is defined because I'm giving you what happened, giving you the output. And if I plug in 1 in here, I get 3. So f defined at 1, condition 1 is absolutely there. Now the limit, when x becomes close to 1. Now the limit here is a bit not problematic. What's happening when x goes to 1? The problem is basically forcing me to split my problem. So I need to compute the limit from the left. I have to, because the function is changing its output, and the limit from the right. So from the left, we have, if x is less than 1, my output is x squared plus 4x. That's my output, that's the rule. And this is gonna give me 5 because it's 1 plus 4. If I'm approaching it from the right, the output now, the rules for the output from the right, I'm strictly bigger than 1. So now this is the 2x plus 1. And the 2x plus 1 is, let's see, 2 plus 1 is equal to 3. So left limit, right limit do not coincide. The limit does not exist. Condition 2 is failing. So here, the right limit is different from the left limit. It means the limit itself does not exist. It means the limit itself do not exist. And I don't know why I boxed myself here. Do not exist. So the limit itself do not exist. It means definitely, and I can go here, f discontinuous, f not continuous at 1. So we don't really need the graph. We don't really need the graph. And what we need, I mean, we don't need it. I'm done. The problem is solved. But now, of course, so graphically, just because we know a lot, not a lot, we know what's happening near 1. This is my 1 here. And the output at 1 is 3. And what's happening from the left, we're getting close to 5. So from the left, we're actually getting close to 5, but from the right, we're getting close to 3. So that's really what's happening. There is a jump right at this stage. So that's really what should happen, but you don't have to graph at all. I'm not really asking you. And now is the question continuous from left or right or neither? So let's see. F of 1 is defined. So now, sorry, I'm asking here. So is it f is right or left continuous? I'm leaving this open and we will fill it out. Okay. So f of 1 defined, of course, we have no issue with that. And let's see which limit coincides with the actual value. The limit from the right coincides with the value of the function. So this makes the function right continuous at 1. So here the limit from the right is the value of the function, which make f right continuous. So it's continuous from the right because the limit from the right coincides with the value of the function. Okay. Any questions about that? Any questions? Okay, so that's the idea of continuity. It's really something that really keep going. That's really what it is. So it never jump at the point, but the word jump is not really mathematically accurate. So we defined it in terms of limit to make the definition very accurate mathematically. Any questions? Okay, now we move to chapter 3, derivative. So today, of course, it will be an introduction, and it's actually a little bit of 2.1 and mainly 2.3, because 2.1, the book used the notion of like kind of tangent line, kind of derivative to motivate limit. And I definitely avoided that. I would do a little bit of 2.1, and then mainly it is section 3.1. And the idea, so the problems, I will assign problems from 2.1, so I don't want you to be confused. Introduction to the idea of derivative. So today, tomorrow, it will be only an introduction, probably the day after, okay? So we're going to study this thing called derivative, the thing, in basically geometrically first, and then we're gonna study it in physics, how they use it, and in general measurement, you know, what does the derivative mean? So today we will study basically the geometrically the idea, but forget about derivative for a little bit. Now we're gonna take a problem that really baffled people for a long time. And this problem was what we call it the tangent problem. So tangent line. So we're going to talk about something called the tangent line. All right. So suppose I have a function. Okay, and this is my function f. And a point, I fix a point. Okay. Now what is a tangent line at a point? So what is a tangent line? The tangent line is a line, straight line. And it touches the curve only at A, right there, at this point. So that's a base point, AF of A. It's a line which is going to touch the curve only here, and it's basically from one part of the curve. So if this curve is concave down, the tangent line intuitively, it's a line that looks like this. That's the tangent line. Okay. And like if the function, for example, is concave up, that's a point A. I fix the point A here. And the tangent line is the line that touches the curve here, but not only touches the curve only at this point, but is from one part of one side of the graph. So when it's concave up, the function, the tangent line sits below the graph. So that's the tangent line at this point. So if it's concave down, the tangent line sits above the graph. If it's concave up, it's a line that sits below the curve. Now, this is about this line. I drew this line by hand, of course, and if you guys draw it, now it's gonna be slightly different. So we're not all gonna draw it the same. Our goal is to find the slope of this line. That's really our goal. So that's geometrical problem goal, find the slope. Find the slope of the tangent line. Find the slope of the tangent line. But here is the problem. This is a line. To find a slope, I actually need 2 points on the line. So let us say I know the function, I know this point, I need another point. But of course, I don't have another point. I'm using my hand to draw this. So there is no other point. So the idea is, what meaning are we gonna give to the slope? And here is what we are going to do. This line is actually very much close to the curve. So when we draw it very, very close to the curve. So the idea is, we don't know another point on the line, tangent line, no way. I mean, I'm drawing it by hand, but I know point here. The idea is, I'm going to take points right on the curve, right on the function. And instead of finding the tangent of this line that I don't really know, I'm gonna find slope of those lines on the curve, which I will be able to do. And then the logic is, as we take points which are close to the base point, those lines are coming closer and closer to the tangent line. So instead of finding the slope of the tangent line, I'm gonna find the slope of those lines right there. That's intuitively what is the idea. And now let us do it a little bit more accurately. So I need to define the notion of secant line, which is, I think we defined before, but now we need it for real. So first, secant line. Okay, secant line. All right. Suppose we have a function f of x. That's a function f of x. And I'm going to fix 2 points on the graph. So f of x is a function, I'm going to fix 2 points. This is a, f of a, so that's the point a, f of a. And I'm going to call it p. And I'm going to take a point here, q. And let us say for now, I'm going to call it b, f of b. Because if this is b, the output is f of b. Then the line, important, the line joining those 2 points, a, f of a, and b, f of b. So the line that joins the 2 points on the curve, this line right here, this line, that line, it has a name. It's a point on the curve, it has a name. It's called secant line. Secant line. Okay. Now, what is the slope of the secant line? So the slope of the secant line, that we usually denote by the following. M, because we use the letter M for slope, PQ, to say that's the slope of the line PQ is equal to. Now, go back to the picture. What's the slope of this line? That's a line, so this purple line is just a line. Now, what's the slope of the line? These are 2 points on the line. It's basically the rise over the run, absolutely. The rise in this case is, if this is f of b and this is f of a, this is f of b, and this is f of a. So the rise is from here to here. So the rise is f of b minus f of a, or the change in output. So that's the rise from here to here. So it's f of b minus f of a, or as you guys have seen before, that's the change in output. And the run is from here to here. That's b minus a, or as we've seen, is the change in x. So the slope of the secant line is nothing more than the change f of b minus f of a, or f delta y, divided by b minus a, which is at some point in the beginning of the course, we called it the average rate of change. Okay, so that's a secant line, and that's the slope for the secant line. So let us say a very straightforward example. So example. Suppose I take the function f of x equal x squared, And the question is, find the slope of the secant line, which is joining the point 1 f of 1, and let us say 1.5 and f at 1.5. So the question is, find slope of the secant line. So it's secant now, that join 1 f of 1 and 1.5 f at 1.5, just to get this straight first. So this is my graph. That's my function. And that's the point 1 right here. And that's the point 1.5. It's somewhere in here. That's 1, that's 1.5. And I need to find the slope of this line right there. That's my line. I'm gonna call this point P, and I'm gonna call this point Q. And let us remember, not only the formula, we have to remember the picture. It's the rise over the run. The rise is the value of the function at 1.5, that's the change in y, minus the value of the function at 1. That's from here to here, because that's f of 1.5, that's f of 1. And from here to here, that's the change in x. That's the 1.5 minus 1. A picture that we will go over a lot. So the slope is the value at 1.5 minus the output at 1 over 1.5 minus 1. So let us compute this. F at 1.5, my function is a squaring function. F of 1 with squaring divided by 0.5. And now we do the math. It means we basically pick up the calculator. That's what I mean by doing the math. We pick up the calculator and we evaluate, which is if I do it, because later on I will be bored doing this. So I take 1.5 square minus 1. I divide this by 0.5. I'm getting exactly to 0.5, which is going to give me the slope of the secant line. Okay? So that's the slope of the secant line. It's simple. It means you take 2 points on the graph and you compute the slope of the line joining them. Now, if you have the function, you have everything you need. Okay. Now we're going to move to slope of the tangent line. Well, I'm slowing down a little bit. Make sure if you guys are copying, you're done. So part 2 is the slope of a secant of the tangent line, which is not very hard actually. All right, so slope of the tangent line. Okay. I'm going to take very specific example. So let me take the function f of x equal x squared, and we're going to find the slope of the tangent line at the point 1 f of 1. So this is my graph. So okay, this is my function here. That's my point, my fixed point. That's 1, and this is my point P. And the goal is find the slope at the point 1 f of 1. And my function is f of x equal x squared. Okay, so that's how the approach would be. We're going to take first a point Q here, a little bit farther away from P. And I'm going to find, so the tangent line is intuitively this line. But that's the best of my ability is to draw it like this. But we're going to really give a really solid definition of this slope. All right, so we start with the point 1.5, and I'm going to compute the slope of this line first. So we'll tell you the strategy and then we proceed. Then I said, but this line and the tangent line are actually kind, so this is my line here, are kind of far. I'm going to take a point then actually closer here. What do I mean closer? Means I'm going to take the point here. Let us say I'm going to take here 1.1 closer to Q. And I'm going to compute the slope of this line. It's just a bunch of slopes. And I'm going to realize as we get closer and closer to P, what's happening to the slope of the secant line. That's really the strategy. So
I have a question real quick.
of course, go ahead.
Where'd you get the 1.5 from, or is that just the next?
We pick it.
Like,
we're gonna pick them. We're gonna pick numbers.
okay.
Yes, absolutely. We're gonna pick numbers which are getting closer and closer to 1.
All right.
And we're gonna find, because we don't really know how to find the slope tangent line. We have no idea. I mean, I'm drawing this line. If you come and draw it, you're gonna draw it differently. So the way we do it, instead of going here, the line intuitively is very close to the curve. So we jump to the curve itself because we understand it. And then we start taking slope of the secant line. Okay? And
all right.
Are you with me?
Yes. Thank you very much.
We're going to make a table, actually. Honest to goodness table here. And I'm going to take point Q close to the point P and compute slopes and see what's happening. So this is the point Q. And this is the x coordinate of the point Q that I'm going to make it very close to P. P is my base point. P is fixed. That's solid. I'm not moving it. That's my base point. And this is the slope. And I'm going to take a lot of points. So I start at 1.5 and I'm going to do everything. And then I'm going to do it at 1.1. And then I'm going to do it at even closer. Let us say at 1.01. And as we did almost with the idea of a limit. And then even closer. But then at some point we feel that, we don't need to do that anymore. So 1.5, it means I take this point. So this is the point 1.5, output at 1.5. So f at 1.5. And now we compute the slope, verbatim. The slope is the slope. We just did it a minute ago. We repeat. It's the output at 1.5 minus the output at 1 over 0.5. Okay, and this will give me the following. What's the output here? For the first one, we do it slowly and then we move faster. The function is x squared. That's I'm giving you the function. It is x squared divided by 0.5. And we did that a minute ago. We got 2.5. Means the slope of this first line here, this one, the slope of this line is 2.5. Now I zoomed in a little bit and I am after this line here. Okay, and I'm computing the slope of this line. So let's do it. I will read myself verbatim. So this is the point now, 1.1. The output at 1.1. And let me compute the slope. So it's equal to the output at 1.1 is 1.1 square. The output at 1 is 1 over 1.1 minus 1. And then the rest is machine. It means we pick up the calculator and we have to do it. So 1.1, but we have to turn it on first. 1.1 square minus 1 divided by 0.1. And I'm getting 2.1. Okay, so I am at 2.5, 2.1. It means the slope of this line right here, this one, is 2.1. And the idea, we are going to keep getting closer to the point. So we do that and see. At 1.01, we know the point. I'm moving to the slope. Equal 1.01 square minus 1 over 1.01 minus 1. Again, I will pick up my calculator. Again, I compute. And I'm going to get 2.01. I keep zooming in, and tomorrow I'll show you graphically what is really we are doing. I mean, what are those? But let's wait for tomorrow. 1.001. So I'm really, by now, I cannot graph it. I'm really right here, very, very close to the curve. I'm right there. And I am actually finding. So I'm going to compute the slope here. 1.001 square minus 1.001. Again, I pick up my calculator verbatim and I compute. I get 2.001. Okay, so now, of course, you're gonna tell me stop. You shouldn't keep going anymore. So when the x-coordinate of q become close to 1, as we're getting the value close to 1, it means as my point q is becoming close to my point p, my slope in this problem are becoming close to 2. So just by really zooming in at the point P, we're really zooming in and we're computing the slope of the secant line. And then we realize that those slopes are becoming close to 2. Now, before we give a definition for the tangent line, your question should be, why did you take all the Q's to the right of P? Why not to the left of P? I have to do it to the left of P. I mean, so this is, I took all to the right of P. The idea is also I have to always to take to the left of P. So what do I mean to the left of P? Means I need to take the x-coordinate of Q less than 1. Like I need to take it 0.9, 0.99, and 0.999. I have to do both. And then I have to compute the slope. So now I'm thinking to the left. I do the same thing. I do the same thing. And then I realize that if I take 0.9 and I plug in number verbatim the way I did here, I'm going to get, let's see how much should we get in here. I do the math verbatim and I'm getting, no, something is not right. Okay, 0.9. So we should get what should we get? Anybody did it faster than I am? 0.9 square minus 1 divided by 0.1. So I'm getting 1.9. Now I got it right. And if I do 0.99, we're gonna get 1.99. And this gives me 1.999. So obviously, as we get close to 1, this is also getting close to 2. So the idea is when we get close to the point P, those slopes, the secant line, are becoming closer and closer to 2. And this will motivate the following definition that we're going to stop at it. And then we're going to say that as the point P become close to Q, the slope of PQ become close definitely to 2. And as P become close to 2, the line PQ is actually becoming close to the tangent line. So this motivates the following definition. So we're going to define the slope of the tangent line at the point 1, f of 1 to be equal. So now the definition, we define the slope to be equal to the limit as Q become close to P of the slope of the secant line. So that's what we're going to do. So we compute the slope of the secant line, PQs, and we ask ourselves what happened when Q become close to P. And in this, so it's the limit as Q become close to P of M of PQ, which is in my scenario here is equal to 2. So our first intuitive definition, which is we're gonna make it more formal tomorrow, is the following. What's the slope at 1.1 f of 1? We compute the slope of the secant line. P is fixed, and we let Q close to P. And then we ask ourselves what happened to those slope. The number we get is what we call the slope of the tangent line. Okay. So that's the first intuition behind it, definition, and tomorrow we will make it slightly a little bit more formal than that. Okay. Your homework will be on my lab for tomorrow. You will have like probably 2 problems from 2.1 and the rest about continuity. And I know you're wondering about your exam. Usually exam take time with me to grade and like your quizzes. So hopefully by the end of this week, you guys will have them. Okay. Any questions before I let go? All right. Bye-bye.